Hello everyone, and thank you for coming along to this talk. My name is Rahil, and I'm a postdoc at the University of Adelaide in Australia. Today I'll be presenting my work with Professor David Paganin on attractor-driven matter. Now, the framework of attractor-driven matter was motivated from the physical system of walking and superwalking droplets. So let me start by describing that first. So if you take a bath of silicon oil and you vibrate it vertically, then you can get a droplet of the same oil bouncing and walking on the liquid surface. So as you see in these videos, each time the droplet bounces, it locally creates a slowly decaying standing wave around itself. The droplet then interacts with these waves on subsequent bounces to propel itself horizontally. So one key feature to note about the system is that there is memory in the system. So since the wave generated by the droplet on each bounce decay very slowly in time, the motion of the droplet is not only influenced by its most recent wave, but also by the waves created in the distant past, giving rise to memory in the system. A simplified model that captures the key walking dynamics of the droplet in the horizontal direction is called the stroboscopic model. So imagine capturing only one image of the droplet per bounce in experiments. So then the motion you would get is something that looks like in this video, right? So you would not see any bouncing motion because you're only taking one image per bounce and you only get horizontal walking motion. So the stroboscopic model does exactly that. It averages over the forces acting on the droplet in the vertical direction and provides a trajectory equation for the droplet in the horizontal direction. So here's the equation of motion for the droplet in horizontal direction in its dimensionless form. So you have the inertia term, so it's basically an F equals ma equation. So you have the ma inertial term. There's dissipation in the system. So you have drag forces. You have a dissipation term modeled proportional to velocity. And then the term on the right-hand side is the force that the droplet feels from its underlying wave field. So this force is calculated through integration of all the waves created by the droplet in its past. And the force on the droplet is proportional to the gradient of the wave field. So in the end, we have an integral differential equation that describes the motion of the droplet along with two dimensionless parameters kappa and beta. Now, the waves generated by the droplet in experiments have both spatial oscillations and spatial decay. Now, if we only retain spatial oscillations and consider a simplified sinusoidal wave field, then it turns out that we can convert this integral differential equation of motion into a finite set of ordinary differential equation. In fact, it turns out that the integral differential equation of motion with a sinusoidal wave field exactly maps on the classic Lorentz dynamical system, right? So you have this nice one-to-one correspondence between the droplet's motion and the Lorentz system, and they are related in a one-to-one manner. So the parameters in the Lorentz system, sigma, r, and b, map to kappa and beta in this way, and the variable capital X in the Lorentz system represents the particle's velocity for the droplet. The variable capital Y is the wave memory force acting on the droplet, and the variable capital Z is related to the amplitude of the droplet's waves at the droplet location. Right, so in a sense, you can forget about the complex integral differential equation for the motion of the droplet and think of the droplet as being a particle whose velocity is driven by the capital X variable of the Lorentz system. So now we generalize this idea in the framework of attractor-driven matter, right? So basically, in the framework of attractor-driven matter, we say that a particle has an internal state space which is governed by a low-dimensional chaotic dynamical system, for example, the Lorentz system, right? And this attractor, internal attractor, drives the particle motion. And then when you have a collection of these particles in some environment, then you can get complex dynamical and collective behaviors. Now, there are four key components in this attractor-driven matter framework, right? So the first component is this internal state space that is modeled by a low-dimensional chaotic system, such as the Lorentz system. The second component are the single particle dynamical variables, such as its position, its orientation, and so on. The third component is the types of interactions between particles, So this can be again modeled in various ways, the types of particle-particle interactions. And then the last component is the modeling of the external environment in which the system resides. Right, so in this framework, these four components can be coupled with each other in various ways. Okay, so let me now show you some examples of attractor-driven matter. So let me start with a simple example of a single attractor-driven particle. Right, so we have the internal state space component A driving the particle dynamic speed. All right, so let us consider our single attractor-driven particle in the context of an active particle. So active particles are particles that consume energy from the environment and convert it into directed motion, right? So examples include fish, birds, or even microorganisms, right? So organisms that are alive, they consume energy and convert it into motion. And there are also artificial systems such as the walking droplet, which is an example of an active particle. So a very simple model of a one-dimensional active particle is the run and tumble particle. So in this model, particle moves at a constant speed and then switches its direction between left and right. So traditionally, this run and tumble particle is modeled using a stochastic dynamics and Langevin equation, as you see here. So the velocity of the particle is equal to some constant speed u, and its direction changes according to a dichotomous Markov noise. Now we can use our attractor-driven matter framework to model a similar active particle. So for example, if we consider the equations of motion that we had for the walking droplet and make a slight modification, so the first equation, x dot, in the walking droplet, x dot was just capital X, right? So if we now modify that to x dot equals some constant u times only the sign of the capital X variable, then what we get is a similar run and tumble attractor-driven particle, right? So when the phase-space trajectory on the Lorentz attractor is on the positive capital X side, so right wing of the attractor, our attractor-driven particle will move at a constant speed in the positive direction. And when it's on the negative side, it will move at a constant speed in the negative direction. And as the phase-space trajectory evolves on the Lorentz attractor, our attractor-driven run and tumble particle will switch between left and right, right? And a typical trajectory can be seen here in panel B. Now, from this, we can calculate the probability distribution of time spent either moving to the left or right between the switches. And this turns out to take the shape of these discrete peaks that have an exponentially decaying envelope, right? And this distribution is inherent to the attractor. So if we change the internal attractor or the way it is coupled to the particle motion, then this will change. And in this way, we can model a variety of different types of active particles from this attractor-driven matter framework. We can also model two-dimensional active particles using our attractor-driven matter framework. So if we now have the orientation variable for the particle being governed by the internal state Lorentz attractor, then what we can do is in the Lorentz attractor, when the trajectory switches between wings, we can have a turning angle for the particle, which is given by, let's say, the z variable of the Lorentz system, right? And if we do this, then we have a two-dimensional run and tumble particle where the particle will run in a constant direction for a while and then tumble according to the z variable. And it turns out that if we do this, we get almost a uniform distribution of the turning angles. All right, so let me end by providing another example of our attractor-driven matter framework. So we'll now consider a collection of attractor-driven particles with interparticle interactions between them. So we consider 2D attractor-driven particles that I presented before. So we add two ingredients to these 2D attractor-driven particles. So each particle's orientation has one aspect where it tries to align in the average direction of its neighbors, and this has some weight given W. And then also with the remaining weight 1 minus W, the particle tries to orient in the direction that its own internal Lorentz strange attractor is telling it to, right? So we have competition between these two effects. So a big sect-like aligning interaction of average direction of its neighbors, and then the particle's own internal orientation coming from the internal strange attractor. All right, so if we implement these interactions and simulate our particles, then what we find is that initially everything is dominated by the aligning interaction of neighbors, and you get coherent flocking, right? This is because the phase space trajectory has not yet settled on the strange attractor, so everything is dominated by aligning neighboring interactions. Now, you will see that a few of the particles now will start leaving these coherent flocks, right? As the particles get on the strange attractor, right? So there you see, right? Some particles are now leaving the flocks, and this is because of, again, that competition between the particles trying to remain with the flock through aligning interaction and then trying to move based on its own internal Lorentz attractor. Right, so because of this, you start getting interesting dynamics coming along. So you will see flocks leaving flocks, colliding flocks, you will see as well. You will also see scattering of flocks and much more intricate dynamics coming from these simple ingredients. Right, so maybe I'll just let you watch this for a few seconds before we move on. Right, so you can see that very interesting dynamics between flocks arising from these interactions. Okay, so in conclusion, we presented this framework of attractor-driven matter where each particle is modeled with an internal state space of a low-dimensional chaotic system. And we showed examples where these attractor-driven particles can model behaviors reminiscent of active matter, such as that complex flocking dynamics that we showed at the end. And then also this framework of attractor-driven matter can be applied more broadly beyond the realm of active matter to model complex dynamical and emergent behaviors in a variety of settings. Thank you for listening to my talk, and you can find more details about our work in the paper mentioned here. Thank you.